All right, friends, so we're going to talk about area enclosed by curves, but we're going to talk about some really tricky examples to visualize. So let's giddy up. All right, so I want to find the area of the regions enclosed by the following curves. So I've got these three examples that we're going to go through in this video, and I'm going to bet that you probably don't know what these curves look like off the top of your head. So kind of the bigger question here is like, all right, what's up with that? What do I do? So, okay, let's start with the first one here. So I have these two functions, and so I don't know what the graphs look like. This, I think, is actually one of the harder ones. So what I'm going to do first is I'm just going to try to figure out where do these two curves intersect. So the cool thing about this is that these are both y equals. So when you have two things that are y equals, that makes life easier because then you can just set the two functions equal to one another and you can solve. So I would recommend, actually, if you're playing along at home here, and I do recommend that you do this, that you pause here and find what you think are the points of intersection before I show you. So what I'm going to do, right, is I'm going to bring everything over to one side. Now this acts quadratic, so this can be factored. So I can factor this as x squared minus 9 and x squared minus 1. And then these quadratics can be factored again. My coffee hasn't kicked in yet, sorry. So I can factor as you see here. So these points, 3, -3, 1, and -1, these are where my points of intersection happen. So here's what I'm going to do. I'm going to note that. So I had this great conversation the other day in class about like, okay, but don't I have to know what the graph looks like? So not really. So we can kind of just finagle this and get this good enough to visualize. So there's where I know my points of intersection are going to happen, right? So these graphs have to meet at these points. And so really then what I need to know is in between each of these points of intersection, which is on top and which is on bottom. So specifically what I mean is, so from -3 to -1, I just need to know which one of these graphs is on top. And they can't switch, right? Because these are the only 2 points of intersection in this interval. If it switched somewhere in the interval, then there would be another point of intersection. So from -1 to -3, there has to just be one curve on top. That's all I care about. So I do have to be able to visualize this, but we can kind of just finagle this. And so what I'm going to do is I'm just going to choose a point between -3 and -1 to help me out with this. So I'm just going to choose y of -2 because that's just right in between. So I'm going to do my calculations for this one in green. So this comes out to y of -2 is -19. And for this one, I'll do it in blue just so we can kind of track everything. And so what I'm going to do is I am just 100% eyeballing this. So here's approximately where -4 is. Here's approximately where -19 is. It doesn't have to be perfect, okay? You just need that reference point. And so now what I'm going to do is I'm just going to draw two curves so that I can really clearly see this. Blue is on top, green is on bottom. Blue, green. Okay, cool. So that gets me the first part of this. And so I need to find this first little area in here. Now I want to keep going with this just so we have a game plan and then we'll start integrating. So now I want to move from -1 to 1 and I want to know which is on top in this case. So okay, once again, let's choose a point between -1 and 1, which of course would be 0. So I'm going to go ahead and calculate 0. Thankfully that's pretty easy with these two functions. So once again, I'm just going to plot kind of a general point. I'm not being super precise. I need to know which curve's on top and which is on bottom. So I mark a point for 0, 1 and a point for 0, -8. And then I'm just going to continue this rough graph that I have here. So now we've intersected here. Might not even be perfectly at this point, but we've intersected and now we've switched, right? So this graph doesn't have to be perfect. You really are just trying to figure out which is on top and which is on bottom, and you just need a good enough drawing. So this is the next area that I have to find. And then if I repeat this process one more time, so going between 1 and 3, so I'll do y of 2. So y of 2 and y of -2 are going to be the same. So it's just going to be the exact same answers. And so once again, I'll have this one's on top and this one's on bottom. So everything's color coded. Okay, so now I have the 3 areas that I really need to find. Now, out of curiosity, if you just want to see, let's compare this to the real graph. So I haven't used any technology to do this, right? But let's take a field trip to Desmos.com. Okay, so this is what the actual graph looks like. But once again, I just want to reiterate here, like, I don't actually need to know exactly what the graph looks like to integrate this. The key things that I really needed to figure out is what's on top and what's on bottom. And I color coded this to match what I have in the slides that I was just showing you guys. So this one is blue. So the right blue function is on top, and then the green function, you can see how it's on bottom, and then it's on top, and then it's on bottom. That's the only thing that I really need to know from this graph. I don't need this like perfect sketch. This is a good enough sketch, and that's what you're trying to do with these types of problems. Okay, so like I said, this is not perfect, but again, it's good enough for what we need. And so when I say that you should be drawing visuals, this is really what I mean, something that is good enough. And that's going to be the theme of this video. So now let's find the areas, right? And we've really done the hard work, so we're going to start here. So in this particular example, since what's on top and what's on bottom is flipping, we're going to have to integrate 3 different times to kind of pick up on the fact that it's changing, okay? So remember, when we're integrating with respect to x, so we're going to take the top function minus the bottom function. Since everything's color-coded in this case, it makes it nice and easy for us to figure that out. So my x squared minus 8 is on top, and then this x to the 4th minus 9x squared plus 1, that's on bottom. And then for my limits of integration, so again, because of how I've drawn this picture, I can really easily see it goes from -3 to -1. Boom, boom, okay? So now we can just integrate. And this is not a bad integral, right? Like the integral itself is not bad. It's usually like figuring out what the beep is going on with the graph, okay? So, all right, we do all that, right? We collect our like terms, we integrate, oops, I forgot to put my limits of integration there, there they are. And then bada bing, bada boom, you plug it in, and then, you know, you get 304 over 15, you know, a nice, a not nice number, but okay, 3/4 over 15, we got it done. That's all that matters. So this little region here is done, and the area is 304 over 15. So now we're going to move on to the next little region, okay? And so now, again, it's that top minus bottom, right? So now I'm just flipping everything. So it's this function now minus this function, and it's going from -1 to 1, okay? And so really, like as far as integrating this goes, so as I go through, I can collect my like terms. This is basically the same integral. It's just all the signs have been flipped. And so you also can like reuse work from a lot of your integration, from like a lot of this integration. So it's not like having to redo all these integrals. Like you kind of already know where they're going. So all my signs are flipped. I just need to plug in my limits of integration. So when I plug in my limits of integration, I get 176 over 15. Okay? And then we go to the last part here, right? And now it's flipped. So let's see. So I've got 106 over 15. So let's do this last one. So this is basically the same as the first, like this is like basically symmetric, right? So we can do a really quick check of this. So I'm just going to quickly breeze through this part. So, so now I've got, there's top, there's bottom, there's my limits of integration. So now I'm going from 1 to 3. But if I go through and I do all my calculations for this, and I've got them all here so you can pause if you want to read this, it comes out to 304 over 15 again, because again, it's just symmetric. So I've got all my pieces now. So boom, boom, boom. So then I just add them up. And so then my area will come out to 784 over 15. Sure, obvious. Anybody would have looked at that and known that right off the top of their head, right? So these are hard because it's hard to figure out what to do with the graph. But like this is doable. You just have to kind of be patient. So now let's talk about something where we have to be a little more creative, all right? So now I've got 9x squared plus y equals 9 and x to the 8th minus y equals 1. Okay, so let's talk about like how you'd probably approach this at first. First things first, I'd probably go ahead and solve for y, right? And so then I'd be like, oh, great, it's just like a. And so then I would start, I would set the two equations equal to one another. And then, it's like, all right, cool. So I'm just going along my business here. And, I bring everything over to one side. And now I'm just going to, oh, wait, I can't factor this, right? So, like, think about this for a second. If you don't believe me, try to factor it. I can't factor it. So this is now going to be a question mark, okay? So think. We're going to have to be creative sometimes in how we figure this out. Now remember, the goal here is for this to be good enough. That's it. We just need to be good enough. So let's go back to the drawing board. Let's look at these for a second. What can you say about these two graphs, like the shape of them, just by looking at them? And I would actually challenge you to pause for a second and just, can you sketch this situation? Like, challenge yourself to do that before I tell you. So pause and hit play when you're ready. Okay, so here's the deal. This is a negative, so this is 9 minus negative, or coffee, I need coffee. Okay, 9 minus 9x squared. So this is a parabola that's opening downwards, but this 9 raises this up, okay? So this brings it up 9, but it's opening down. And then x to the 8th really acts like x squared. So this is a parabola that's opening up, but it's been moved down 1. So by the way, this like relies on your understanding of some just like pre-calculus stuff. So if that's something that you forgot, you might want to go back and like review that. I think I'll drop a link to a review video on that if you forgot kind of the code of reading functions. Okay, so anyways, this, like I said, this is a downward, this opens down, but it's been moved up 9. This means it's moved up 9. And then for this other one, so now this has been moved down 1, so we'll say this is moved down 1, but it opens upwards. So it's something like this, right? And so once again, this is that spirit of this is good enough because what do I really need? I need to know which one is on top and which one is on bottom. So this is good enough. Okay, cool. So I set this all up, but then, what are the intersection points, right? So we have this whole problem, right? Because we couldn't find them earlier. All right, so again, creativity. We want to stop, think. For calculus, one of the things that we're trying to get over is like this, I'm just going to give up and not know where to go with this, okay? So you have to now like spend some time like thinking about the equations and staring at them. And so the thing that like I kind of notice is like, okay, I don't know where these intersect, but one thing that I just kind of notice in just inspecting these is what happens when y equals 0. So there's a question for you. If you don't know what happens when y equals 0, maybe you should pause and figure that out before I tell you. So if I plug in y equals 0, so I get this situation here, 9x squared equals 9 and x to the 8th equals 1. And so when you solve this, actually, you get at y equals 0, this is going to be this is going to be plus or minus 1. So a lot of times with these functions, like you can kind of inspect them and make some observations. And a lot of times it's going to be around something like kind of obvious, right? So looking at the graph that I had here, I know that it's going to kind of cross somewhere like this. And then if just kind of playing around with this, I could see that at y equals 0, that's going to happen. So this kind of just comes from being like curious, sitting with it, and being okay with it. And the theme of calculus very often is just try something. Just see what happens. Like, you're not going to know the answer right out of the gate. I know it's frustrating, but like this is the bigger point of calculus is for you to learn to sit with that frustration and push through it, all right? So we have pushed through it. So I can update this graph. And so now I know that these points, these graphs meet at 0, y equals 0. This is the point -1 and 1. So now I've got my two limits of integration. Hooray. I haven't had enough coffee for me to be as enthusiastic about this. Maybe I'll try again. Hooray! Okay, that's a good one. So now we just integrate that, no problem, right? So usually the integrals are not really that bad. It's like, how the heck do you figure out the limits of integration or all that other stuff that's tricky? All right, so now I've got everything kind of plugged in. You know, from here, I just plug everything else in and I get 124/9. I would make sure that you get that as well. But that's what this is going to come out to. Okay, and I have one more here. So this is another one where it's like, I have no idea. When I did this, I was like, I'm not even bothered trying to figure out what this graph looks like. So this one's weird because it's x equals 3 sine y square root of cosine y. And this is enclosed between this, x equals 0, and then y falls between these values. Okay, so like draw this out of what this part here means, because this is gonna mess with you, okay? So I've got my X and Y axis. There's where X equals 0 is. And where does Y fall between? 0 and pi over 2. So where is that? There's 0, there's pi over 2. So we're talking about this region in here, okay? But also like we're talking where X equals 0. So let's zoom in on the part of the graph that we care about. So like this is what I mean. Like you need to like sit there, draw, think. Like you might have a couple of drawings before you zero in on what it is that you're looking at. But now we're good. And now I just have to think of like, okay, so what is the deal with this graph? I am not going to figure out what this looks like. I'm not going to spend my time on that. I don't care. I'm going to think about what happens for these values of y when I plug them into the graph. So what I notice is from 0 to pi over 2, so sine of y from 0 to pi over 2 is positive, and cosine of y from 0 to pi over 2 is positive. So I'm plugging in, right, I'm plugging in y values. So what that tells me is that all of these x values have to be positive. So the values of these on this interval will be positive, so x has to be positive. All right, so what that means is where is my graph going to fall then? So here's x equals 0. Is my graph going to fall over here or over here? It's going to fall somewhere over here. And like I said, I don't have a clue what this graph looks like, okay? But it's somewhere over here, and this is good enough. So all I care about is good enough. I thought it might be fun just to take a look at Desmos real quick, just to see. I don't know what this graph looks like. So like you can, sometimes I think it's nice to look at technology just to see what some of these weird things look like. So let's look at Desmos real quick. So here's the graph. And so remember, we are just doing this from 0 to pi over 2. So we're just dealing with this little portion right here. And so my graph is good enough, right? Because I just, like, the big thing that I need to know is that there is just something on this side of the graph. That's good enough for me to integrate. So yeah, my graph looks nothing like this, but it gets the spirit of what the point of the problem is. All right, so now, good enough. What do I know about integrating in this case? So in this case, I need to integrate with respect to y, right? There's no way I can solve this for y, so I'm just going to deal with this being in terms of y. So when we integrate, we take the rightmost function minus the leftmost function, right, with whatever our limits of integration are. So this is the general idea that I want to use. And again, like just for my purposes, I can really easily tell this part here, which represents my very whack drawing of the function, this is the rightmost part. So it's going to start with this minus the leftmost part, which is 0. So this is going to look like just this function here. So this is all I have to integrate. And I'm integrating from 0 to pi over 2, right? That was almost like a freebie in the problem. And so now here's what I have to integrate. And so now this is like the most interesting of integrals out of this whole video. So, you know, I can set my u equal to cosine of y. My du will be equal to negative sine y dy. Bada bing, bada boom. I'm going to go ahead and change my limits of integration. So I've got everything all set up here. And so when I go through and I evaluate this, now I've got this nice simple integral to go through. And ultimately, I will get that this whole thing just equals 2. Whew. All right. So things to think about. Hopefully this helps you with figuring out kind of how to get good enough with your sketches. If you found this helpful, I would love it if you hit that like button or maybe the subscribe button or leave me a comment or share the channel with your friends. That'd be real cool. Otherwise, I'm going to leave it at that, guys, and I will talk to you later. Bye.